So, today we're going to do on-chip communication systems. It's a bit different than originally planned, where placement, routing, and timing came. But I decided to do this way around and switch it from the original plan, because it's a bit more of a concept again and less of theory. So basically we can then implement something new, and next time then we can analyze an overall design. And then we have the last two sessions, which is anyways more exploratory tasks where we will need all of until today and also next week, although we need in the last two topics essentially. On-chip communication systems is essentially what everything is connects to each other. We want to answer a few questions. So basically, what are those systems? Why do we need them? What different communication protocols? Well, bus systems we have, so less protocols or like packages types, because it would be another layer on top of it. What factors do we have when we select? How do these architectures impact our system performance? Master and slave roles, just as a recap, importance of arbitration, and in a very short manner as well, and then how do we test and verify and test and simulate that. So let's see if we can answer all of these. From introduction, this is the assignments or the previous assignments roughly in the block diagram. So we have on the right side peripherals, for example. We have a buffer in form of a first in, first out, or FIFO. And in our previous assignments, we have an arbiter here. So to like select which signal goes where. There's only one unidirectional for now, so we assume here would data come from, or this would have produced data. There's something behind there. So this is just as a recap. Now we would like to have like something which generates data, like a central processing unit or something like this on there. And the question is, how do I, for example, interface between the arbiter and a central processing unit? Because the CPU needs some way of standardized interact with it. In reality, this is actually done through a so-called interconnect network. So the central processing unit, and I can maybe actually show in the end of the lecture, I forgot that I could just pull the examples from actual architectures. Basically has a CPU, and on top of that, the CPU has a lot of interfaces. So it's just the processing core has always a lot of interfaces with all the different things. And this is usually called an interconnect, and this interconnect then can be connected up to all of these, and then all of these processing units, or these FIFO peripherals or whatever it is, and then you have addresses for each of them, and then you can address them and reach them. You can of course also, we're going to come to this is a bus system in this case, we can also make it a point-to-point or entire network or whatever. So we have on the chip our own communication interfaces, and usually you want to standardize them as much as possible because it makes it more efficient. And what allows us to do as well is then that we have here standardized blocks. So we can have here the same bus interface, all of these blocks, and we just give it different addresses, and then we have very simply everything routed through. So ideally, maybe our communication protocol, which we send to the peripheral, would include it as well, and then we could just decode it according to the bus, which the bus automatically already can do, and then this makes it all very simple. The next option is, of course, to add then all kind of other blocks, for example, data reduction, interpretation, encryption of signals or whatever, to the system, and then we can also just connect to the interconnect, and then everything is on one bus system. I'm going to come to the downside of it. Of course, it's like a bottleneck if you put everything under one bus systems, but it's also kind of nice because you do not have to write any interface anymore. So what we had in the very beginning, that we have just arbiter, we have signals, 1,000, as you can remember in the previous assignment, which all different signals, you can now bundle them together in a bus interface, and this makes your architecture and also your debugging and those kind of things much easier, because if you always use the same, what you want to call an interface wrapper for your bus system everywhere the same, then you have to just verify that part yourself, and you just gotta make sure that your bus system to your FIFO or to your whatever block you have as processing or whatever it is working well. So of course that's also beautiful for testing and simulation. Gonna come to that in the end. So that's why we have those. It's not gonna be a too long lecture either. And this allows us really to evaluate a lot of these things. It's very useful. In the beginning I hated them because I didn't understand them. It can be quite complex. You're gonna see that in a second, but it's useful. So essentially it's the reason why we have this as kind of described just now. Sufficient data transfer between IP cores, standardized interaction between diverse design blocks. Of course, not every design block and every IP core uses the same communication interface. So of course, maybe I need sometimes a converter or wrapper on top of that, or I need to find another solution. But we're not going to dive into that today too much. And it is always, I mean, I do not know, and it probably is one, but it's always used for a CPU memory controller, like, how's it called? RAM access and those DMA, direct memory access, sorry, that was a word, DMA or DSP blocks or sensor input, so you always wrap them in there. And very often, like literally for Xilinx devices, you will get automatically a CPU which has an AXI interface, which we're going to come to what that means. And we have always also a DMA memory controller for DDR3, DDR4, or whatever, so that's quite convenient. So we have this directly accessible, we don't have to write this ourselves anymore as an IP core. And then we have various communication types, of course point-to-point, a shared bus like I showed before, and then of course there's a network on chip where we have an entire bus system network of different points, like a small web essentially. Good. Here again, point-to-point is a direct link between, just as a recap, I think that's, if anyone has done network technologies or something like this, it's quite obvious. It's point-to-point is directly between two IP cores. It's perfect for the minimal latency, but also limited scalability. Every time you want to connect something else, you will have to make a new bus interface. Use cases is basically everything high-speed, low latency. So it's everything where you have a lot of data throughput, for example, again, a DMA memory access or those kind of things. So the processor, for example, is more common to have a full bus because we will allow you to just do anything from the processor. So usually you do not have that super much communication between the CPU and your programmer logic because programmer logic is anyways going to be faster. So you do not want to send this data back and forth, otherwise you're going to be making your CPU busy with all this data. The shared bus is between multiple IP cores. For example, if I have a data flow, very common, or I do not know in a standardized way that one thing flows to another, to another, I might want to have the flexibility to have addresses in multiple areas and then access to that. And of course, we have here an arbiter, as we also programmed a bit ourselves. But they can be much more complex because they can have at the same time the same signals. We have all not implemented into the arbiter for those who looked a bit more into that code. Yes, in general purpose, as said, for example, simpler designs or for a CPU or something like this, where we do not know the exact purpose of our bus system. Of course, also has a more overhead than a point-to-point, just because it requires an arbiter, addresses, and all these kind of things. A network on chip is basically a mix of both combined, so it's not a hybrid, it's a network of multiple of those on top of options essentially. And so basically it's entirely scalable to whatever you want because you're going to use multiple shared bus and multiple point-to-point. And then you can have, in this web, you can have high bandwidth data paths, plus so-called either control bus systems, which allow you to then configure small settings or change the one register in this one IP core, which changes the data which then flows through your point-to-point network. So this goes then into higher complexity designs with more system on chips with many cores, so multiple CPU cores. And then you really have to start thinking about what you want to use where and so on. Is this the overhead? Do I need this latency? Do I need this throughput? What bandwidth and so on do I want? Yes. Boring slide, just for the theory, to kind of give a bigger context of what all exists. We're going to focus on Umber, because it's just what's most used. I've used the other two in the very beginning when I started, but since then I've neither worked with Intel, Altera FPGAs, not much at least. So you have Avalon, but you also can always put an Axie on there. Which one is open source, you might want to consider that. But the big standard is like really ARM's Umber standard, which is right now this advanced microcontroller bus architecture. And the Umber Axie 4 is the state of the art right now. There's an Axie 5 that I have not seen in any software yet. For example, Xilinx has fully adopted Axie 4, so every IP core, wherever you have it, is almost all entirely Axie 4, except for like smaller blocks like a FIFO. They do not necessarily have a bus because it would be too much overhead. And then you write a wrapper for the FIFO and the entity which you have behind. And then just for reference, so when you see those, that you know where they're sorted, because I've worked with APB and HP as well. They are predecessors, so they're Umber 3 or Umber 2. So they were used, for example, in ARM Cortex-A, or and Umber 2 was used in ARM 7, 0, and the Cortex-M. And basically here you have from Umber, you have HP and APB, which then was upgraded, and then upgraded again with HP, and then for Axie 4, they started to actually have a portfolio of 3 different types. I'm going to show them in a second, or like as well, we're going to spend most of the lecture on, is basically where everything kind of got unified into different purposes, and they're very distinct. And they also, when you have them once, you will use them. It's quite standardized. Wishbone, open source standard, just an alternative to avoid potential licensing issues. It's a simple master-slave architecture. You can look into that if you want. Although, for example, Xilinx devices, you would need to write it for everything yourself, or would have them to write wrappers from Axie to Wishbone. And Avalon, I've only seen that in the end. I always avoided and went to Umber standards. That's just Intel FPGA, and as a proprietary one, like ARM, but much less used, much less open. This also, just for a fun fact, this is not actually Intel. This comes from Altera times. So this was something which Intel bought in when they bought Altera back then. And it's not because Intel didn't like Axie. So the Axie 4 series, it's probably what you're going to work most. If you work with older designs, you will come to HP and so on. But the principles are very similar. I mean, they're all Umber standards, so they're going to look similar from understanding. We have 3 Axie 4 series types. We have a full Axie, which is the one, for example, when you connect on a Xilinx device, you connect your processor or your system on chip processor to the rest of your programmer logic. Then this will be Axie 4. I've mostly worked actually with Axie 4 in combination with Axie 4 Stream, Axie 4 Lite with Axie 4 Stream, because you have a controller entity and then you have a high throughput. So you can also do it like this. And it's generally a burst-based protocol. So you configure on each communication how many bytes you want to send with one burst, and that can be flexible. And it has read and write operations based on these bursts. From architecture, it's quite simple. So we have a master interface which will send an address and a control command, so basically where to go to and what I should do. The slave will react and will then send the data back. So this, for example, for the read data channel. For the write channel, you would send, of course, address and control, and you would send the write data afterwards. Yes?
So the master sends an address to the slave, so the slave knows where the master is, right?
No, it's to find the slave. So it's the address of the slave. There can be multiple slaves, and you will need to have an address to know where the signal should go, right? So basically, every slave will check if this is the address, my address, and then I know I'm being talked to, and I will send a response.
Okay, so it's a broadcast.
Yes, in that sense, yes. And yes, for reference, of course, a lot you can find, of course, in the official Axie interface documentation. but also for you to study Wikipedia is a very extensive source, and there are a lot of primary sources. So in this case, you can definitely go through that. So there's a principle of Axie in general. We're not going to dive too much through this, and it's just that you have seen those diagrams. So we have like a bus system clock, so basically each clock cycle will have this where the data is being differentiated or tested essentially. It's a synchronized system, of course. And then you have an address. We have, for example, here the address size, or how much data we want. And we have the data which we want back, and then we have an incremental, so there's different burst modes. I'm not going to go into that, it's going to blow it all up. But basically we have then some validator, some acknowledgement, and basically we then get from the read data channel the data back, and we get an OK signal. And then according acknowledgements for which one is the first, so if we're valid, so if we're ready, or if we're lost. So it can be, for example, that our slave needs time to load the data out, so then the ready signal would vary. It's something which you have to implement and interpret them as well. So these are, for example, the read channel signals, and we have also write channels. So you see have a lot of signals. Also, of course, connected to the clock. We have a writing address where we want to write to with the size of that, the length of our data, versus incremental, and then we have again some acknowledgement, handshakes. So handshake is very important here because otherwise the data will be dismissed, at least in the proper documentation and implementation. You can always say I do not care about my handshakes, but then you have a problem. And then we write the data, we acknowledge this, and then we get also a response that everything was all right. In very simple terms. Very often I would recommend to actually go to tools like something System Vivado. You can just write literally they will give you a wrapper to make an IP core into an Axie IP core automatically. So you can just click through that. That's also what's going to be, the assignment is going to be around. So basically you have your design, and we put it all into the wrapper, and then we have to code it up a bit. We'll see how I facilitate that. That's not too much to code from a workflow point of view. Yes. So simple protocol. It's quite advanced. It's quite efficient. Axie Lite is basically a simplified bus for a register and changing in control of a system. It is not meant to transfer any significant data. So it's reduced features and complexities, so it's one beat only bursts, which means it's only one byte usually, or the bus data bus bandwidth. And this bandwidth is also limited to 32 or 64 bits. And this makes it kind of nice. It makes it very efficient from our overhead because there's no other signals for or no change of remaining signals. And basically what I can do is I can just request, I can just write to a IP core the data, or I can request one register value. So I can always have an insight into the system, and I can always very nicely control it. And that's of course something quite useful, especially if you have, for example, more complex IP cores and you just want to control them. And also nice, of course, and that's why I say why I kind of like Axie, and I think is why it's also the standard. So almost everywhere it is compatible with Axie for sort of full mode. So this means that I can have Axie Lite slaves everywhere, and it will just, as long as I have the same signals and interpret it the same way, if the Axie master sends the correct values, it will perfectly interact with Axie Lite. So I do not need to have any converting logic or any adaptations to integrate Axie Lite into my overall Axie network. Yes, so quite simple. That's actually what I started with, because it's much easier to understand because it's compressed and you have to do less coding yourself if you get started. Axie Stream is high-speed data streams. And guess what? It's the point-to-point version of Axie. So you do not need to have any addresses, no handshaking. No, it's also only unidirectional. You have no bursts. You have, instead of bursts, you have data packets and frames in streams. So this goes onto the protocol level then. So on top in your data is then identify what is the start. So if you have an image, you would send a beginning of image, a header, the image data, potentially a footer, maybe some checksum, and then an end of image, and this would be facilitated on that level and not through the communication bus itself. Of course, that adds some overhead, but also you're much faster, because of course also the burst length of the normal axis is limited, which is in this case not the case, so you can just have a continuous data stream. Again, this is why it's being used for direct memory access or any high-speed communication, because it's just connecting 2 points to each other. And then we have the other important part is that basically the bandwidth needs to be an integer number of bytes. That's the only constraint. Makes it quite simple from that point of view. When we then have these different options, for example, we have a lot of different factors. What do I use? Where? When? How do I use it? What implementations do I use? In general, you want this is a beautiful tool to standardize your interfaces and your workflows. So ideally, you write once, or you get somewhere a very nice AXI interface from, and this will make it perfect, because then you have everywhere you have the same AXI implementation. You know that this one is very optimized for timing, resource utilization, and so on. So if you have a thought out concept, you will have very good latency. So you might want to use if you have something mediocre where you have like data and just control on it, you want to use the full AXI. But if you just want to trigger to get data and then get a very high response, then you have least overhead with an AXI line and an AXI stream, and then you get basically the lowest latency with the highest throughput. But it's something which you always have to trade off. Network systems are not always never that simple that you can just choose the one or the other. You want to use probably a mix of it. Timing constraints is very important if you when these bus systems get long, in a sense. So if they go through multiple sections of the chip or go over an entire chip, especially if your chip becomes very big, you will have few timing constraints, so the signals actually reach in time the other side. That's something to consider. And but usually the routing tools will accommodate this, but having a well-optimized IP core for your bus systems will help you here a lot. So if you write it nicely and keep it simple and not multiple logic elements per clock cycle, then you're good. We will come to these optimizations next week, etc. Then we have bandwidth allocation and arbitration. So of course we need to kind of coordinate on our system how everything works. So what kind of arbitration do I want to use? Do I even need one? Do I have multiple systems which talk at the same time? So I need to kind of think of what my system does, how much it's being utilized, and of course this also then plays into the latency and throughput. How much is my system being utilized? So I have to should think about it before. How much data do I want to send through my bus or through my chip? And this will then decide on how fast my design is. There's no point in using whatever wide AXI stream if I just have 1 byte wide data, and that's for half of the time. Still, maybe worth it to use an AXI stream, but think about the overhead, how much you actually need, because this again will eat into your resources, which eats into your timing, and all these kind of things. Of course, and then goes into power consumption. Yes, so really well optimized and thought out concept for these kind of things leads to a much better design. Of course, in many cases, already using bus systems will make it a better design, but you can of course always push the limits there a bit more as well. Maybe also sometimes it just doesn't make sense to use a bus systems. There's something to decide when you do your design. So it's always in FPGA, when I've learned something, having actually early on a draft out on what interfaces do I have, what speed do I need, how much data throughput I have between the different blocks. Figuring this out earlier rather than later will help you to really early decide on how efficient, and you do not have to change. And it allows you, as previously said also in the last lectures, allows you to do test benches analysis of the design, which device you want to choose, and those kind of things. Yes. In general, we use this, as I said, to interface IP cores and FPGAs. Just some general things. Master and slaves. Master initiates communication, so the slave just responds to the request. I think that's common knowledge, I hope, in this course. And the multi-master system is common. So there can be multiple masters on one system, and then you have to have an arbitration, and that's why we need an arbitration, because we can have multiple masters speak at the same time, and then you need to have either some kind of arbitration which basically tries to resolve the conflicts when they try to access the system. So you can either queue them up, you can give them priority, you can let them cycle through, you can do time multiplexing, you can do a lot of different things. We can talk about it a bit if needed, but AXI implements one on their own. You can configure this. If you want to write your own bus system, then we anyways beyond the scope of the lecture. So, that's fine. IP cores, that's basically where the other design considerations before. And that's actually the most important one. What interfaces do my IP cores already offer? We have talked about it, I think, in the very beginning. FPGA designs of IP cores can be not the latest because they've been written a long time ago and there's just no need to update it. But it might mean that they use AMBA 2 and an AHB or something like this, or an APB or whatever, and then how do I make this compatible? Maybe you decide because of this that you want to use on the overall system AMBA 2 or AMBA 3, so use AHB. And of course that's a valid option. But you also see, I can do everything else with AXI, so AMBA 4 would be much more efficient. I have only one thing which I have to convert. So you're going to convert across the one. That's something, again, which you have to look into in the beginning. Which bus systems do I have? Where do I want to have maybe split networks? Maybe I have a few AMBA 3 IP cores and some AMBA 4 IP cores, and then I can just split them in a communication. I have just one bridge in between them. So very commonly it is used to make bridges between two communication systems to make them work with each other. So it's kind of a router between different communication protocols. So I need to look into my requirements, matching signal data bandwidth, time requirements, very important. So what kind of clocks do I need on which side of the bus systems? Do I have different clock domains? Also very important. So I need to have a clock domain crossing potentially. Gonna come to that, what that means next time. But really gotta think, this is, when you come to communication systems, you have to have your full system in mind. You can, of course, when you just do an IP core, maybe you just want to make it an AXI 4 standard, simple, so everyone can use it as they want. But if you see my IP core, let's say, would never require a lot of data throughput and it just needs to be controlled because it does something magically on its own, then you just want the other interface anyways goes somewhere else into a sensor, then you might just want to use an AXI 4 Lite to reduce overhead on the IP core. Maybe you also want to provide different options for your customer. So you have a version of your IP core with AXI 4 Lite, AXI Master, and so on. That's also something which should be considered when doing your designs. Also, what is AXI 5 and so on? That's still kind of being developed. There's not much difference on so far which I found. So AXI 4 for now it is. Yes. I forgot here to, I guess I have to look at it. Oh yeah, so arbitration techniques. Round robin, so it's a buffer essentially priority based. So I always select which is first. Has of course a problem if I have a high priority bus which clogs everything, nothing else gets through. Time division multiplexing. What is the entire debate of what you want to use? Is my priority that important that I may lose data? Because it's always gonna one bus is gonna go through. Then towards the end of the lecture here, simulation and verification. Bus systems are standardization of communication, so it's perfect for simulation because I do not have to write the logic for any interaction of every IP core. So that's kind of nice. So what I just have to do is actually build a tool which loads my data from whatever file into my test bench, and then this test bench will read out my data file and puts it into your bus system. So it's kind of nice. Of course, when I do simulation, there might be some interaction on my control side, but at least I do not have to worry about controlling the control side into the IP core, because that's what my bus system does. Also, there's many test benches already for the bus system itself. There's many open source options available, so you can find online AXI IP cores, AXI IP core / simulation, and means also they can be part of your IP core. So in Xilinx and in Vivado, you have actually options to simulate your AXI core. We'll look a bit into that. And really analyze your performance, because we had this before, that you may not need the throughput or the latency or the bandwidth utilization. And that will be quite an overhead, that you have a lot of data, a lot of bandwidth, which you will never capitalize on it, and then will use a lot of resources on the chip. So it's something really to be considered, and that's something which is then possible through my simulation and verification. So if I see my bus system almost never runs, when it's running, it's not even using everything, then I might consider to reduce it, especially if I have overall timing problems on my chip. I said not too long. So definitely we just covered here how it's tested and verified. Look into the standardized test benches, they exist. Should be used. You can of course write something on top of that, but every time you write your own test bench, you've got to verify that you didn't make a thought mistake. And if you write a bus system and the testing for it, that's going to be difficult. I think we're clear why arbitration is important, because we have a multi-slave system, a multi-master system. Master and slave is clear, and how we can impact the performance for this. If you use the wrong interface or the wrong communication interface, we're gonna make our design so much worse. If I use an AXI Lite, when I have a lot of data, then I will never get done with the data, because I have to send 1,000 requests. I did the mistake once. So something which can happen when you just underestimate or you do not fully understand the systems. And I think it's also really clear why we select certain things and why we need the different bus systems. Good. That was already it.